connecting rod. This is our crank, all right? So as this comes down, it pushes this and this thing turns. And we can either go counterclockwise or clockwise. For this one, we'll just imagine it's going this way, counterclockwise. So this is, let's say, coming down. This is going to push us down, go around, and then come back. So I'm giving you some dimensions, that this is 2 inches and that this connecting rod is 8 inches. And I say, how fast is the crank turning in RPM? So what's the revolutions per minute of this crank? If the, and I didn't write the word in here, this is supposed to be, if the piston is 9 inches from the crank bearing. So I'm saying if the distance from here to here is 9 inches. Do y'all agree that when this piston is at the very top that the distance would be 10? Do y'all understand that? If I turn this like this, then this would be 2, and then from here to here would be 8, and so the total distance would be 10, right? So I'm saying, no, not then, but at some other point when this is 9 inches from here, I'd like to know at that moment, how fast is that crank turning? I'm trying to give you a problem that you could actually see maybe in the real world as opposed to a cone being filled with water, you know? I mean, this is more like real life. Yeah. You definitely drink water out of a conical cup, like that does happen, but not many people wonder how fast the water level is coming up, right? Here, if you're an engineer and you're trying to design an engine, you want to know how these rates are related to one another, right? To get the best design. All right, got it? All right. Sorry, I've missed something important. I'm telling you how fast the piston is moving down, 300 inches per second. So I'm telling you that when this is 9 inches right here, at that exact moment, this piston is coming down at 300 inches per second.
So would that picture be a general?
This is, right now, it's a general picture. Yep. All right, I'm going to take this off the screen. Is that all right? Leave it for a minute or what?
1 more second.
1.
No. No. Okay, then I need the picture.
Okay, I'm gonna move on. So here, I'm gonna draw it again, all right? But my picture's not gonna be like a piston and a crank. I'm just gonna do points, all right? So here's my general picture. In general, I have the piston up here, right? I mean, imagine that's a piston. Then I have the crank arm, which comes down like this to a point. And then I have the crankshaft right here in the middle. I know that this is 2 and that's 8. And do y'all agree that that's never changing? Right? Those distances are not changing. Yeah? And I can measure the distance between here and here. Will that distance change?
Yes.
Yes, right? That depends on where this is as it spins around. I'll do a little dotted circle around this so that you can remember. This is moving around in a circle like this as this piston point moves up and down, right? That goes up and down, and then that spins this around. So that distance doesn't change, right? So let's label it with a variable. I'm going to use, I'm going to use y. I don't know why. I'm going to just use y. Okay, so the y is that distance, right?
The y is the one that changes.
Y does change, yes. Do you agree?
Yeah.
Yes? Okay. So that's my general. How about the instant in time? Maybe I can do that now. At the instant in time, we have the point here. We have that this is 8, that's 2, right? That's 2, that's 8. But now at the instant in time, we're talking about when this is actually 9. That's the instant I'm talking about. What am I given? What do I want? So do you want me to put the problem back up? Yep. Do I give you anywhere in the problem, do I give you a speed of something?
Yes.
Yes, 300 inches per second. That's the speed of what for us? Whoa. It's the what? Whoa. Okay, it's the speed that this piston is moving downward, right? If that piston is coming down, this point doesn't move, does it? So it's really the speed of that point coming down. Doesn't that tell you how fast y is changing? Right? If I tell you that point's coming down at 300 inches per second, then that means y is changing at 300 inches per second. Right? Is it growing or shrinking? It's shrinking. Y is shrinking. So I'm going to put negative 300 inches per second here. Do you all understand that?
Yes.
You have to remember that when this point moves, the piston, it only goes up and down, right? It doesn't like come over here and do anything, right? It doesn't change. It's just up and down, up and down. So y shrinks and grows, shrinks and grows, shrinks and grows. And at this instant that it's 9, we're saying it's coming down at negative 300 inches per second, or it's shrinking at negative 300 inches per second.
So if it was moving up, that number would be positive?
It would be positive, yeah. But I said in the problem it's moving down. All right. What do we want?
How fast is it going?
We want the RPMs, right? Revolutions per minute. Revolutions per minute. Revolutions per minute. How are we going to do this? You could say DR for revolutions. The problem with that is where's R here? Where's revolutions on our picture? There's no revolutions, right? What is there in our picture, though? Something that has to do with revolutions. Okay, circle. If I start, I'm going to get sick here, but if I start doing this, right, I'm doing so many revolutions per minute, right? What's changing other than my equilibrium? An angle, right? I have an angle that's changing over time. Do y'all see the angle that changes? As this piston comes down, this goes around, and do you see that that angle starts to change? Yes? I'm going to label that angle theta. And so what I want to know is how fast that angle is changing with respect to time at exactly the moment that y is 9. Now, if I get an answer d theta dt, that's not revolutions per minute, but I should be able to convert into revolutions per minute. Let me put it this way. What if I told you that I spin 360 degrees in 1 minute? Then what are you going to tell me my RPMs are? 1 revolution per minute, right? So there's a way to get from degrees per minute over to revolutions per minute. We'll have to think about that a little bit more in a minute. All right, for now, let's just see if we can get d theta dt. Y'all good? Any questions? We need an equation, exactly. Something that connects the theta in my picture to the y in my picture. Unfortunately, that is not a right triangle. It looks like a right triangle here, isn't it? But if I drew it a different way, like if I drew it more like this, right? Like that's a different point in time, right? That's definitely not a right triangle, is it? So I can't use any right triangle trigonometry or geometry for this. So can you all think of any time in your life that you were working with triangles, you had two sides, an angle, and well, you've got an angle, you've got a side here, some way to connect this all together?
This is like S equals R theta.
That would have to do with arc length. You have law of sines and law of cosines as well. So why law of cosines?
Because you have two sides.
Yeah. All right, so let's see if we go back and look in your formula sheet. What does the law of cosines say? Law of cosines. It says that if you have a triangle, and I'm not sure how they label it on your formula sheet, but They say if you have a triangle, it does not have to be a right triangle, there's a relationship between these sides and these angles. The first, there's 3 different relationships you can draw from it. It's all there, right, on your formula sheet. One of them says that little a squared equals little b squared plus little c squared, what? Minus 2bc times cos of big A. Here's the thing about this formula. This formula requires that you have all 3 sides and 1 angle, right? Do we have 3 sides in this picture? Yeah, we don't know what y is, right? But we have 3 sides and we have the angle, right? The law of cosines brings all of those together into one equation, which means that'll be an equation that has theta and y in it, won't it? Okay, so I'm going to use that one. Now, I need to change it to match my picture, I guess, a little bit. So why don't we call, let's see, we have to be careful here. The y is like the c is in that problem. Let's say that's the c. Let's make the a the 2. Hold on a second.
Does it matter?
It doesn't matter, but I want it to match that formula. There's 3 equivalent formulas, so let me change this. Hold on. What angle do we have? Here it's A, right?
Yeah.
Here it's A. So that's the side across from that angle. So I want this 8 to be my A, right? If that 8 is my A, then that angle, theta, is like the A in that formula. So A and then the side across from it. Then the other 2 are B and C, and it doesn't matter which one you pick. B, C. I'm just doing that to help you see how I'm going to plug it into the formula. Got it? All right, let's plug it in. So according to law of cosines, it's going to be a squared. For us, a squared is what? 8 squared, 64, equals, okay, b squared. What's b for us? 2, so square that, you get 4, and then plus, what's c squared for us?
81. It's y.
It's y, yeah, not yet, not 81 yet, right? We can't fix it here. We have to be looking at this picture. So the c is the y, so it's y squared, right? And then minus, all right, what's 2 times b times c?
Negative 4y.
2 times, so it's 2 times b is 2 times c is y. Okay, negative 4y. And then cosine of theta for us. So y'all see how I've applied the law of cosines to that triangle? It's not pretty right now, but do you agree this is an equation that has y and theta in it? Yeah, and therefore I can differentiate it, and I will have a dy d theta. Sorry, I will have a dy dt, and I will have a d theta dt, which is what I'm working with here. But I'm going to clean it up first. This is 64 equals 4 plus y squared minus 4y cosine of theta.
Can you move that 4 over?
Yeah, I'm going to move the 4 over right now. Subtract 4 on both sides. 60 equals y squared minus 4y cosine theta. There we go. I'm going to box that. That is an equation that connects y and theta together, which is what I was looking for. But I had to dig through and grab the law of cosines to get it, right? Would law of sines have worked? It would not have worked. Because for law of sines, you need 2 angles. You have to go back and look at the law of sines. It basically says that sine of A over little a equals sine of B over little b, but that's the same as sine of C over little c. And then you could also just flip all these over and it's the same equations. But if you work with any 2 of them at the same time to create an equation, unfortunately you need 2 angles, and we only have 1 angle on here, theta. That's all we have. So that's why I didn't use law of sines. All right. Now we are finally at the calculus step, right? Like everything up to this point has just been set up. Now the calculus, I'm going to differentiate this with respect to time. What's derivative of the left side with respect to time? 0, right? So 0 equals, all right, be careful here, derivative of y squared, 2y, and dy over dt. Good. dy dt. Chain rule, right? First the power rule, and then you take derivative of the y. Okay, I'm going to do it this way. Minus, I'm going to leave the minus. And what I want you to do is look at this right here. I want the derivative of that, which is going to require the product rule, right? I could have put the 4 out here with the minus, but I'm just going to leave it in there. And I'm going to do a product rule here. Derivative of the first one times the second, plus the derivative of the second one times the first one. And I need to put this in brackets or something because I'm going to keep that negative sign on the outside. So what's the derivative of 4y?
Negative
4.
Oh, for what?
Yeah, ignore the negative for now. What's the derivative of 4y? 4. So 4 comes for the ride. What's the derivative of y?
4 times cosine theta.
Hold on. What's the derivative of y?
dy.
dy dt. Now times cosine theta. So there's the derivative of the first one times the second plus, yeah, the derivative of cosine theta. Now we got to be really careful with derivative cosine theta. I need to erase this part so I can fit this in here. Okay. The derivative of cosine of theta is negative sine of theta, right? But don't forget the chain rule, right? You've taken derivative of cosine, now you need to take derivative of theta, which is d theta dt. What happens if you forget that part?
Then you won't get
You'll never get what you're trying to solve for, right? Which was the whole point of us having an equation with theta in it. All right, are we done with the product rule? I'm missing something. What am I missing at the end of that? I did the derivative of this, right? Times the first one, 4y. So I need a 4y here. All right. Do you all agree that that was my derivative? Now let's start looking at things and see if we have what we need. I'm gonna erase this. I'm gonna go back up to this line right here and make that a minus 4y right here. We differentiated this, right? That was our equation, but we had moved that over, so it was 60. That's what we had differentiated, right? Let's run through it again. Derivative of that's 0. Derivative of that's 2y dy dt minus, now product rule. Here's my product. Derivative of the first one is 4 dy dt times cosine theta plus derivative of cosine theta is negative sine theta times the derivative of theta, which is d theta dt, times the 4y to finish off the product rule. Do we have everything we want? Let's see. Do we know why? Now we can fix everything. I can look at this picture. Do we know why at this moment in time? Yes. Do we know dy dt? Yes. Okay. Do we know dy dt? Yes. Do we know cosine theta? No. Could we get it though? Because look, don't we have theta right here? And don't we have 3 fixed sides? And if I have 3 sides of a triangle, I can definitely find the angle. And I'm going to actually use this formula to do it right here, right? Imagine I told you what y was. Then could you solve for theta? Yeah, you could. It's going to be a little bit of a pain in the ass, but we can do it, right? So we don't know this right away, but we will be able to get it. Do we know sine of theta? Again, no, we don't know what theta is yet. But I know I can get it. I can get it from this. D theta dt. Well, that's what we're looking for, so I'm happy to see that. Okay. Y, we already said y was 9, right? So there's, everything there is either something we have, directly we have what it is, or indirectly we can figure out what it is. So what do you think I should go after right now?
Solve for theta dt.
We are going to solve for d theta dt, but we need to figure out what these are, right? Which means, how about we go find theta?
Yeah.
Can we go find theta? Let's go find out what theta is. And I'm going to work off this picture right here. And I'm going to use the law of cosines, this equation right here. And we know that y is what? 9. So if y is 9, right, then that equation becomes 60 equals 9 squared, 81, minus, what's 4 times 9? 36 cosine theta, right? That's that with 9 plugged in. And now we're back in pre-cal, and we're trying to figure out what theta is. So order of operations, be careful here. I'm going to try and solve for theta. So first I'm going to subtract 81 on both sides. I get negative 21 equals negative 36 cosine theta. Negative what? Where? What?
Wait, what happened?
Do what?
Oh, yeah.
Oh, yeah. Negative 29.
Where?
Instead of negative 21.
We got negative 21.
Oh, what am I, well, hold on. What are y'all doing?
Yeah, 81 minus 60 equals
That's negative 21. Yeah.
It is
Negative 21? What were y'all saying? Someone was saying something else?
60 minus 81 is negative 21. Yeah.
Okay, all right. So, okay, I thought I heard someone say something, but we're good then?
Yeah.
Okay. All right, I'm trying to get theta, right? So I'm going to get my calculator. Did I bring it? Yes. Okay, because I'm going to need to figure out what this is. All right, so I'm going to divide. I'm going to take negative 21. I'm going to divide it by negative 36, right?
So that would be a positive.
It'll be positive. I've got about, I'm going to use as many decimals as I can here. Right, that's cosine theta. You all still with me? Okay, how do we get theta now?
Don't you have to do the inverse?
Yeah, we're going to use the inverse, right? Now, we have to be careful when we use the inverse, because when you do an inverse, you have domain restrictions. And you have to go back and remember from pre-cal that when it comes to theta with cosine, you're trying to do inverse, your domain restriction is between 0 and pi. So this is only going to be valid, our answer is only valid between 0 and pi. It's only going to give us an answer between 0 and pi. But I'm going to do cosine inverse on both sides. Cosine inverse of the left side. And cosine inverse of the right side just gives me theta. And this actually matters what mode you're in on your calculator here. So what mode do y'all want to be in? I don't care. Do radians? Okay, let's do radians. So I'm in radian mode. I'm going to do inverse cosine of that number. And I get 0.94, let's go with 8, I'll round 3 decimal places, is approximately what theta is.
But you could do the inverse of negative 25, 1 over negative.
You could have done the inverse of all that. I just got that. I did that as a decimal first and then then did the inverse. We should get similar answer.
Why doesn't it matter if you use radians or degrees?
We just need to know that this is in radians because we're about to plug this. Remember we were trying to figure out what cosine theta was and sine theta? So if we get that answer and it's in radians, right? But then we plug them in and we plug it in degree mode, it's going to be wrong. We just got to make sure we keep our calculator in the correct mode, right? So if you're going to do radians here, you better stick with radians when you come back over here to figure these out. If you wanted to be in degrees, how do we convert to degrees again? How do I convert that to degrees?
180.
Multiply by 180, divide by pi, all right, if you wanted to. Or you put your calculator in degree mode and do the same problem and it'll give you the answer in degrees. All right, so now let's come over here and I need to know what these two values are. What's cosine of theta and what's negative sine of theta. And now we know what theta is, right? So I'm going to go on my calculator and let me do cosine theta. We already know what cosine theta is, don't we? What is it, 0.58333?
Yeah.
We didn't know what sine theta was, though. 0.5833. Let's just go 33. And then sine, I need to take sine of that. So that, I'm in radian mode. I'm doing sine of 0.948. And it's negative, right? Negative sign. So I'm getting negative 0.81, let's say 2. Did you do the inverse? Yeah, careful. All right. I am ready to plug everything in. We should be getting close to an answer here. Can I erase all this up here? All right, so I have 0 equals. All right, 2 times y was 9, right? 2 times 9. What was dy dt? Negative 300. Okay, minus the bracket. 4 times negative, this dy dt, negative 300, times cosine of theta, which we found to be 0.5833. And then we have plus, well, actually it'll be minus, won't it? Well, but then there's another, well, no, there's, who cares? Plus, then I have negative 0.812, and then d theta dt is what I'm solving for, and then times 4 times y, which was 9. Close my bracket. There we go. D theta dt is in here. That's what I'm solving for. So I just got to make sure I get this all right and don't mess up anything. Any questions? So we have 0 equals negative 5,400 minus, okay, bracket. Let me do these 3 together there. So 4 times negative 300 times 0.5833. I get negative 699.96. And then when I put this together with this, right, these two together, it'll become a minus, right, because there's 2 positives and a negative, so this will become minus 29.23, and then d theta dt. We're getting closer. Any questions there?
So you got 4 times n and you multiplied that by.
Yeah, because these are all multiplied together. So I did that times that times that. And because this one's negative and those are positive, it became a minus here. All right, now I'm ready to get rid of the brackets. So I'm going to distribute the negative through. And when I do that, I get 0 equals negative 5,400 plus 699.96 plus 29.23 times d theta dt. I'm getting really close now. Okay, so put these two together, right? And when I do that, negative 5,400 plus 699.96, I get negative 4,700.04, and then I'm going to take it to the other side. Yeah, added these two together, not this one. This one's attached to that with multiplication, so I can't touch that one.
Oh wait, are you supposed to change back to degrees?
No, no. No, no. You're just doing that plus this.
Oh, we're not different.
I got 47,
I got
4,700.04. Yeah. Negative though, right? When you put these together, it's negative, but then I move it to the other side, and that it becomes positive. Okay, we're almost there.
And then
Divide. Take that answer and divide.
You said that it was a negative, correct?
Yeah, but he moved it to the other side.
I moved it to the other side. I get 160 point, let's say 8, is approximately equal to d theta dt. Yeah, now we need the units. Does everyone follow all that? All right. What are the units on this? Radians, right? Angle is radians. Radians per second, right? So here's what I've got. I've got 160.8 radians per 1 second. That's the same way as saying radians per second, right? The reason I did that is because ultimately I want my answer in revolutions per minute, right? So I'm going to do a what we call dimensional analysis, where I start multiplying by the conversions to make this turn into revolutions per minute. So let me start with the seconds. How do I get rid of seconds and convert it to minutes? 60 seconds in 1 minute. So I put 60 seconds here, and I put 1 minute here. And that'll get rid of the seconds, and I will have minutes. And how do I convert radians to revolutions? So 1 revolution is 2 pi radians, right? Go all the way around the circle, that's 2 pi radians. So we're going to get rid of the radians. I need radians on the bottom, and I need revolutions up here. There's 1 revolution, there's 2 pi radians in 1 revolution. And that gets rid of my radians. And so I'm going to do 160.8 on top times 60, then divide by 2. Or you could say 160.8 times 30. Leave the what?
You said divide by 2.
Oh, 2 pi, sorry. Divide by 2 pi. I said 2. You're right, I said 2. So 160.8 times 60. Divide that by, make sure you do 2 pi in the denominator. I'm getting 1535.5 RPM. I'm just going to put RPM. RPM. About 1500 RPM.
Are both the answers that you got here and over here, are they approximate or are they exact?
They're approximate because I'm sure we were rounding, right? We were rounding in.
Wait, RPM is revolution per minute.
Uh-huh.
Okay.
So we have revolutions here in the units here that never got canceled, and we had minutes here that never got canceled. So it'll be revolutions per minute. That's RPM. That's what RPM stands for. Yeah, that's what it stands for. So when you look at your little gauge on your car and it says, you know, your gauge on your car, your tachometer usually has, it's marked like 1, 2, 3, 4. This is in thousands.